Hi everyone, it's Mrs. Moss here. Now today we're going to get started talking about energy in Earth processes. Now when we talk about energy, we're defining it as the ability to do work. And the Earth receives energy from two sources. The first one, as you can probably guess already, is the sun. The second form of energy that the Earth gets is from its core, or the interior part of our Earth, which we'll learn about more in detail as we progress through our topics of discussion this year. But for right now, when we learn about energy, we need to understand that energy is radiated or given off from the sun to the Earth and also from the inner core, reaching the Earth's surface. So it helps drive and sustain life. Now, all matter radiates or gives off some form of electromagnetic energy. And this is going to be seen when we talk about energy and wavelengths and how the energy travels from one location to another. Now, all of these wavelengths and all of this energy that the sun is giving off is known as the electromagnetic spectrum. The spectrum is all of the energy, and we categorize that and classify the energy based on its wavelength. Now, what you'll see is if you get out your reference table, and I'd like you to pause the video and take that out and open to page 14. On the bottom of page 14, you will see the electromagnetic spectrum. Now, your version does not have scientific notation along the top like this diagram does, but this diagram does a good job of showing you the different forms of energy that are emitted from the sun that we receive on Earth. And they go from wavelength, from decreasing wavelength, which is a shorter wavelength which has more power, packed with power, all the way through to the weakest radioactive energy waves, the radio waves or the microwaves. Those are all increasing in length, and it is not as much power involved with those. So the Earth radiates infrared heat, and that is known as, on the electromagnetic spectrum, as infrared. So infrared and heat are used synonymously and interchangeably. You're going to need to know both terms. Each type of energy on this electromagnetic spectrum is divided by its wavelength, just as I mentioned before. So you see it's classified from the shortest wavelength, or the decreasing wavelength, all the way through to the increasing wavelength. Okay, so we go from decreasing to increasing. Now let's talk a little about what wavelengths really are and what they look like. Here's an increasing wavelength. Here it's, as it's going towards the left-hand side of your diagram, they're getting shorter. So if you notice, they look like coils or springs, and the closer together these are, that designates as shorter or a decreasing wavelength. The farther spread out the wavelengths are, that means the wavelength is increasing and actually losing power as it stretches or as it does that. So one wavelength is measured from crest to crest or from trough to trough. We call the top part the crest, as if you may have heard that from surfing, the crest of a wave. That's considered the top part of the wave, from top to top. That's how we measure a wavelength. And the trough is the bottom to the bottom. That's what we will designate it to be, either a short wavelength or a longer wavelength. So the frequency is how many wavelengths move past a certain point in a given amount of time. So if it takes a while for wavelengths to pass through an area, then that wavelength is probably a longer wavelength. If a shorter wavelengths pass through that same spot, you're going to get more waves hitting that area, making it more powerful. So you can see in this diagram how more wavelengths at the top are passing through this white space. On the bottom, the longer wavelengths will take less amounts of frequency to pass through that same white space. So the shorter wavelength is a higher frequency, making it a more powerful wavelength, and the longer wavelengths has a lower frequency. And here's that picture of the wave as I mentioned. The short wave is higher frequency, long wave has lower frequency. And we see the waves with the crests from top to top. Again, if you turn to the page 14 in your reference table, you see that the shorter wavelengths are the gammas, the X-rays, and the ultraviolet rays. Now, you know this because when you get X-rays at the dentist, you need to wear a lead cloth or an apron. That's to protect you from the X-ray radiation. It's a little more powerful than if you were just standing around with your cell phone. Your cell phone, if you notice, is on the other side of the electromagnetic spectrum, and so therefore has a less power to it. So it's a little less dangerous. Ultraviolet rays we know are powerful because you all have to wear sunscreen when we go outside. The UV rays is what's hitting us from the sun, and we need to protect ourselves against it. Let's move on and talk about the way that the wavelengths transfer and go through the atmosphere and through space. Short wavelengths are mostly absorbed by our ozone in the stratosphere. You may have heard about that too. So this line, this gray line in the diagram, is actually acting as a barrier. It's our ozone in the stratosphere, and it helps to absorb those UV rays. And that way, all of the impact that the wavelengths could affect us, it gets cushioned or absorbed by this ozone, so not as much of the wavelengths hit our Earth. So it protects us. Now, in this whole electromagnetic spectrum, believe it or not, this very, very small amount right here between the UV and the infrared, this small amount is the visible light spectrum, and it goes from violet through the rainbow, Roy G. Biv, to red, okay? Now the red, you'll notice, is on the increasing wavelength side, so that is a longer wavelength. You'll notice too that the violet on the opposite end of the spectrum has a shorter wavelength. So those type of colors that are emitted when gases are given off are going to be a little more powerful. Now visible light passes through the atmosphere with the greatest intensity. We see all colors. We see red, we see yellow, we see green, we see blue. So that's how we know that we get most of the electromagnetic spectrum that passes through to us is visible light. More makes it to the Earth. Infrared is important to know because infrared is heat, and that's given off by our Earth. So in this diagram, you see that all of the visible light coming into the Earth, but when you see it hitting the Earth, it gets absorbed into our Earth through the oceans and the land, and it leaves as infrared. That just is basically saying that once nighttime comes and there's not as much sun hitting the Earth, we, the Earth, give off heat energy. Similar to that cable box that you have at home. When you use your cable box and you turn it off, it still has heat coming out of it, right? Well, it's almost like that. The sun works all day, heats up the Earth, and then at night, the Earth then radiates heat back. So you're going to need to copy this down in your notes. Make sure that you get every one, and if you need to pause to fill it in, that's okay too. So we have interactions between electromagnetic energy and the environment that we need to document as well. Pause the video and get this down. These are the 5 different ways that the wavelengths go through our atmosphere. It can be absorbed, like UV rays are absorbed by our ozone. We have reflection. The snow, the clouds, the ice, the water will actually reflect that energy back out into space. We have scattering, okay? The scattering of the energy by certain aerosols or water droplets, once it hits our atmosphere and it hits those droplets or crystals or dust or pollen, it can scatter the energy to go into different directions. We also have something called refraction, and that's when the light that comes in from space will get bent as it moves through the different densities within our atmosphere. Lastly, we have transmission, and that's when it's passed through a medium. I'm just going to skip through this so we can get to our last slide. Okay, and so now we have the different ways this moves. If you can on your notes, we want you to draw pictures of the arrows and how they are moving under the line or within the line, okay? This will demonstrate to you what the different rays do once it hits a substance, whether it's in our atmosphere or whether it's in our ground. It will react in certain ways. So hit pause and take a moment to write this down. Less than half of the solar by radiation is received at the Earth's surface. So that means between our sun and our atmosphere and our ground, a lot of different things can stop the UV energy hitting the Earth's surface. Less than half of solar radiation is actually received by us. Pretty interesting. You see here our atmosphere kind of acts as a shield against a lot of strong radiation that comes from the sun. So we're very lucky in that sense. It comes in and it goes out as infrared, or it gets reflected or absorbed. Now that's going to be the end of our first part of learning about energy. We're going to continue on energy, the topic of energy, in our next video. Okay? Make sure you get all of your notes down. Go back, rewind, re-listen to something I said if I spoke too fast, and ask questions tomorrow when you see us. Take care.